Alright, so we'll be doing the counting principle. People have been wanting this thing for the longest time, so I'm sorry I am actually doing this a bit later than anticipated, but I thought, why not? Better late than ever, right? Better late than never. Better late than crazy never. Just a sec, I want to share this with some peeps just a little bit. Let me just, give me a sec. Yeah guys, welcome in, and I'm sorry for actually coming in a bit later than what I had expected, because time-wise, didn't think. How many people have done counting principle at school and they understand it very well, and they're like, I understand counting principle, I am good, so that I know that I don't have to waste my time and do this with you guys. How many people are masters of the counting principle? Grade 12s, come on, come down here in the comment section and let me know that I am a master of counting principle. If you can just let me know in the comment section, I'd really appreciate, so that I know whether I should do this or not, I wouldn't want to waste your guys' time. Okay, so it seems like people are good. Yeah, so that means people are good with the counting principle. Yeah, very good. Okay, no, that's very good to know, guys, that you are good with the counting principle. You guys are amazing students. Hopefully you guys will do well then, given that you are good. I think I'll end this live because I can see that counting principle is beautifully done, beautifully sorted. People are sorted for years. Yeah, but let me just do it for the sake of those that probably do need it. Thinking of people that may absolutely without fail need it. Okay, so if you are in grade 12, then I'm guessing you are at a good place. Just so that we can recap, I know that most of you would probably feel like for you the counting principle, you are sorted, you don't need any sort of going over. But what I'm going to do is I'm going to go over the counting principle as if you guys have never ever done it ever, and I'm just going to unpack it one step at a time. Some of you may have already done this and you feel like you are good. Please don't waste your time and be in this live. Go and do those sections of the maths that you feel like you still need to work on, until you can actually find me in this live doing the section of the work that you really want me to do. But today I'll be looking at this grade 12 probability counting principle, and we'll see how it is that it is done. So this is grade 12. Welcome to the live. This is grade 12 counting principle. My grade 12s know this topic very well, or this section of the work. So let's look at it and let's unpack it one bit at a time. So this topic says, or at least the definition here of counting principle is according to the following format. This definition, guys, is taken from the Mind Action Series textbook, the new Mind Action Series textbook. All right, and it basically says, in essence, if task 1, now please take note of the use of the word here. It says if task 1 can be performed in N1 ways, and task 2 can be performed in N2 ways, then the number of ways in which both tasks can be performed is N1 times N2. In other words, I'll repeat again. If task 1, so let's just say there is a particular task 1 that we have, and it can be performed in N1 ways. Another way of looking at this is like saying if there is an event, all right, if there is a what? An event, and this event has different outcomes. I think this is very important. If there is an event and this event has different outcomes, this is another way of looking at the very same statement. So this one is saying if task 1 can be performed in N1 ways, it's like saying if an event can be if an event has different outcomes, all right, and task 2, meaning another event, can be performed in N2 ways, has other outcomes, then they are saying then the number of ways in which both tasks can be performed is N1 times N2. So if you want to know the number of ways in which these tasks were performed, then what you do is you multiply the number of respective ways, N1 ways times N2 ways, and in that way you will be able to know what is the number of ways in which both tasks can be performed. So the product gives you that. Okay, the product of the number of respective ways will give you the number of ways in which both of the tasks can be performed. So let's look at an example so that we can actually, I'll go back to the definition as we go through each example so that you guys can appreciate what this definition means as it relates back to the example. So here we have it. A couple decided on the following menu for their wedding reception. Okay, so obviously a couple probably gonna get married, decide on a following menu, and it's for their wedding reception. Guys, hopefully we're not thinking of getting hitched anytime soon, right? But it says a couple decide on the following menu for their wedding reception. So in their menu they have one starter, okay, and then these are the outcomes for the starter. Okay, so this is like an event. Okay, I mean, sorry, not an event. Yeah, it's like an event. So a task, all right, remember I said task can also be referred to as event. Okay, so if you remember, it says if task 1 can be performed in N1 ways. So if task 1, which is the starter, can basically have these number of ways: garlic snails, chicken liver, calamari. Okay, so this would be task 1. This would be the ways in which task 1 is represented. It's like saying if this is the event, then these are the different outcomes of the event. I hope that makes sense. Then you have the main course, which is another task. Okay, let's say you would say it's task 2 if you want to, or you'd say it's another event. And if you look at the ways, okay, that this task is available, or the outcomes of the task, we have these different outcomes. For the main course, you have the grilled king clip, you have the beef fillet, you have the lamb shank, you have the chicken cordon bleu, you have the vegetarian pasta. That's the main course. Then you have another task here, or what we refer to as an event, And in that we have how many ways? All right, we have the ice cream with chocolate sauce, a creme brulee, we've got the Malva pudding, we've got peppermint crisp tart. Okay, so if we look at each task, because this is task 1, this would be task 2, this would be task 3. And I guess you guys know that in a particular wedding reception, to have a starter and to have a main course and you have a dessert, these are things that happen. These are different tasks, right? And we refer to them as different events, and they happen, at different times. But for each task, these are the number of ways or choices that you have. We have garlic snails, chicken livers, calamari. So if I was to ask how many ways can we represent the starter, you would say we can represent the tasker in 3 ways. And then if I asked you how many ways can you represent the main course, then you would say 1, 2, 3, 4, 5. There's 5 ways in which you can be able to choose from the main course. Then how many ways are represented by dessert? Or how many ways do we have represented under dessert? We have 1, 2, 3, 4. So all in all, we have task 1, which is our starter. We have 3 ways. Main course, which is task 2, we have how many ways? 5 ways. And then dessert, which is task 3, we have how many ways? 1, 2, 3, 4 ways. Okay, now we are being asked now how many different meal combinations can be chosen. So if a person was to come now, how many different combinations can a person choose from this actual menu? Okay, right. So if we go back now to the definition of counting principle, it says if task 1 can be performed in N1 ways. What is that? Task 1 can be performed in what? In N1 ways. And task 2 can be performed in N2 ways. Then it says, then the number of ways in which both tasks can be performed is the product of the respective number of ways. So if we want to know how many ways in which can the tasks that we have be performed, then we have to multiply the number of ways together of each respective task. Then we will be able to know how many ways are actually possible. So if we look at this menu again, I said task 1, which is the starter, 3 ways that we can actually serve the starter. Main course, which is task 2, how many ways to serve the main course? We have 1, 2, 3, 4, 5 ways. Dessert, which is the last task, task 3, how many ways do we have to represent or serve dessert? We have 1, 2, 3, 4 ways. Now they are asking here, how many different meal combinations? In other words, how many different ways can we represent a meal combination? Okay, how many different meal combinations can be chosen? Okay, so what we do, guys, is that when we want to answer this question, all right, okay, for instance, I can give you an example of one meal combination. You could have as your starter a garlic snail, and then maybe a grilled king clip for your main course, and then your dessert can be ice cream with chocolate sauce. Guys, that's one meal combination. The question that is being asked is how many different meal combinations can be chosen from, and so what we do here, to use the definition of counting principle, it says if task 1 can be performed in N1 ways and task 2 can be performed in N2 ways, then the number of ways in which both tasks can be performed is N1 times N2 ways. So what we do there is that for each respective task, we are going to actually, because we have 1, 2, 3 tasks, we are going to provide 3 open spaces for the 3 tasks. These lines here, 1, 2, 3, represent what? The 3 different tasks. Each independent task, starter is for this space, main course is for this space, dessert, is for this space. Now what we do now is that since we have identified the tasks that we have 3 tasks. Now we need to check how many ways can each task be performed. So for the starter, for instance, how many ways do we have in total that the starter can be represented? And that is where you actually write down your number of ways. Guys, there's only 3 available options, or 3 ways in which the starter can be served to us. So we say 3 for the first task. Then we move on. The next question is for task 2, how many ways can we have task 2 or the main course served to us? So if you count, there's 1, 2, 3, 4, 5 of these basic ways that we have that the main course can be served. So we're going to write there 5. Okay, and then lastly, the third task, because this is the last space that I have open, that I have available for me for the task, then I ask myself, how many ways can the dessert be served? There is 1, 2, 3, 4 possible ways. So we are going to write 4. Now, according to the definition, what did they say? If task 1, this is task 1, can be performed in n1 ways. Now my n1 ways now has a specific value because I know that my starter can be served in how many ways? 3 ways. So I'm no longer talking about a general thing here. I'm talking about a specific thing. My starter can be served in one of 3 ways. So there's 3 possible ways. There we have it, 3. And task 2 can be performed in n2 ways. What was my task 2? My main course. How many ways do I have available to serve the main course? There's 1, 2, 3, 4, 5. So there is my 5 there. Then dessert, which is task 3. Now in the definition, they only talk about task 2. But remember guys, doesn't matter. We could have 3 tasks. We could have 4 tasks, 5 tasks. The counting principle makes provision for all of these tasks. But the final thing that we need to understand is that when we want to find out the number of ways in which all of these tasks can be performed, what do? We multiply the respective number of ways. Then we can know what is the what? The ways in which all of the tasks can be performed. So what are we going to do now? Since we know that starter can be served in one of three ways, main course can be served one of 5 ways, and dessert can be served in one of 4 ways. What do we now do? We simply multiply the what? We multiply the number of ways that each task can be performed. And then we get our answer of what? Of how many ways, okay, these meal combinations can be represented. So if you multiply the 3 times the 4 times the 5, what do you get? You should get an answer that is, and I'm going to wait for you guys to tell me in the comment section what is the answer that I get, because that will give me an indication of how many different meal combinations can be chosen. Thank you very much. You guys are so generous. 60. So there are 60 different meal combinations that can be chosen in this wedding reception. So this is the beauty. So let's think about this practically. You come to this wedding reception and you are like, I want a variety of choice. I want to have a unique meal in that particular wedding reception. This couple has made available 60 different meal combinations that you could have in their wedding reception. And if you are talking about variety and choice, I would say that this couple has done a very good job of ensuring that the people that are attending their wedding at least will have a vast choice to actually make of meal combinations. So I hope this makes sense, guys, in light of the definition that we have looked at, okay, with this example. Okay, so we're gonna move from this example. Okay, it's very basic, but that's what we want. We want to actually get the concept of the counting principle in our minds and hearts, so that when we start doing, okay, other problems, and exam type problems, we can at least know the basis from which we are answering the questions, because this comes from the definition of counting principles, that if task 1 can be performed in n1 ways and task 2 can be performed in n2 ways, then the number of ways in which both of those tasks can be performed is n1 times n2 ways, and that is the basis through which we were able to answer how many different meal combinations can be chosen, because for each one of these 3 tasks with the respective number of ways that we have, we multiply those respective number of ways, and then we get the total number of different meal combinations that can be chosen from this particular wedding reception that people will be attending to, that this couple is having. Okay, let's go to another question so that we can actually explore other things pertaining to counting principle. Look at this question and the wording, guys. Please take note of the wording. This particular question says, a particular person wishes to have grilled king clip as his main course. And the question now is, how many different meal combinations can he choose? Now, immediately when you read that, you are like, okay, now there's a person who is in this wedding reception attending, and this person is very particular when it comes to the choice that he wants to make with the main course. All right, but we are being asked here, a particular person wishes to have grilled king clip as his main course. Now the question is, how many different meal combinations can he choose? So this person, all in all, what are we being told about him? That he just wants for his main course meal to have grilled king clip. Doesn't want beef fillet, doesn't want lamb shanks, doesn't want chicken, cordon bleu, doesn't want vegetarian pasta. Okay, so that means we exclude and we just restrict our choice to grilled king clip where the main course is concerned. So in other words, what are we doing to our task number 2? For task number 2 alone, we are limiting our choice to grilled king clip. So that means for main course or task 2, we have one way of choosing, and that is grilled king clip alone. But does that affect starter? No, it doesn't. So that means we still have our 3 available choices or ways. Does that affect dessert? No, it doesn't. It means we still have our 4 choices or ways available for us. So all in all, we still open 3 spaces for 3 tasks. And then, as you have beautifully said in your answers, guys, which I'm very proud of, we still will have 3 here, because this man choosing, or this person choosing to have grilled king clip as the main course, just only restricts his choice to 1 for the main course. All right, and it basically excludes everything else. We take out all of this from the equation. We only have grilled king clip. So we'll go directly to the place where we are restricting, because we have 1 available option, 1 way for task 2. Then what about task 3? Task 3, we still have our 4 available dessert choices available to us. So that means we are going to have 4. Then what do? It says kaloku there in the definition, if those respective tasks can be performed in those respective ways, then the number of ways in which those tasks can be performed is the product of the ways. So what's 3 times 1 times 4? And as you guys beautifully said in the comment section, NK Tremzi said 12. So we have 12 different meal combinations, and that is what we were talking about. So you guys are 100% spot on when it comes to that. So we have 12 different meal combinations. You see, so our choices now are reduced because of the fact that, at least for this guy, his choices are reduced to just these different meal combinations. And actually, furthermore, for the main course, he is not going to be choosing any of these, which is why basically now we reduce the different meal combinations that he could have available for his choice. Okay. NK, beautiful. And all those people that actually did well. Okay, let's go on, guys. So that there just is getting us introduced into the concept. All right, I just want to thank Mr. N there for the rose, and also who's this let's see for the 5 roses, and also Tebucho, thank you so much, really appreciate those sweet roses. Rosie. Okay, let's come here, guys. Now we are going to look at a condition here which we refer to as when repetition is allowed. Okay, when we allow repetition. Okay, now we are being asked here, how many 4-digit codes. Now hopefully we can come back and just establish what these terms mean. How many 4-digit codes? Okay, now guys, a 4-digit code it's sort of like a pin. You know how when you're about to open your phone, you usually have a pin number that you actually have, and it usually some people will have a 4-digit pin number, if you want to call it that. Even with your bank card, if you want to get access to the funds in your banking account, then you will have a 4-pin digit code, if you want to call it that. Now, yeah, so if we say 4-digit, then it means there's 4 numbers, 4 secret numbers that you will type 1, 2, 3, 4, and then it will give you access, whatever access that is. Even for some people that have safes in their home, if you have a safe, all right, and you have a sum of money stored away somewhere, those would basically also be utilizing maybe a 4-digit code which you would type in so that you can get access to whatever is in there. Okay, so I just want us to understand what we mean by how many. When it says how many 4-digit codes, all right, we are referring to something like that. Okay, now we are being asked here, how many 4-digit codes using digits 0 to 9 are possible if each digit may be used, and this is the keyword, any number of times. Any number of times. How many 4-digit codes using digits 0 to 9 are possible if each digit may be used any number of times? Now, we want to establish first and foremost what is our task, all right, and the ways that we are talking about here, all right. So when they say how many 4-digit codes, that simply means this. It means that we have 1, 2, 3, 4 tasks, all right. 4 tasks, because a 4-digit code, obviously, a 4-digit code, all right, is basically a code that has 4 numbers. Okay, now we are being asked how many 4-digit codes using what? Using digits 0 to 9. Now the question I want to ask us, all right, immediately, so that now we can establish the ways in which we can be able to fill in each task. The question is, if we look at the digits 0 to 9, how many numbers are we talking about when we say digits 0 to 9? How many numbers? Okay, right, guys are very good there. People are saying 10, all right, and I hope that is very clear for us there, because we are going to build here obviously a 4-digit code, but we are going to be using the digits 0 to 9. Okay, because I was asking how many digits do we have. If we're saying we are using digits 0 to 9, how many digits are we talking about? Here, Rotendo, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So how many digits are these? okay, is the $1 million question. Okay, so hopefully you understand now. Okay, so that's why we say there are 10 digits. So in other words, we are going to be checking how many 4-digit codes can we actually create from the numbers 0 to 9. And here is the condition. If each digit may be used any number of times. So here we are being clearly and explicitly told that repetition is allowed. So we could basically use the digit 0. If we use it here, we can use it there. We can use it there. We can use it there. It's not a once-off thing, okay? If we want to use the number 1, we can use it there. We can also use it there. We can also use it there. We can also use it there, because repetition, as we are told, is actually allowed. Each digit may be used any number of times. All right. So then the question is, how many digit codes, how many 4-digit codes can we be able to have? Okay. So I'm glad that we know, all of us, that 0 to 9 is 10 digits that are possible, because sometimes it's a common error, because I don't know why sometimes people think that, hey, 0, they don't really take 0 into consideration. Okay. So I'm glad that at least we actually all see that. Okay. So if you think about it then, guys, you remember I said this thing is saying how many 4-digit codes are possible if each digit may be used any number of times. Okay. So can we all then agree that in this space, it means I can put 0, I can also put 1, I can also put 2, okay? I can also put 4, I can put 5, I can put 6, I can put 7, I can put 8, I can put 9. That means I have in my first task 10 ways that are available to me. 10, guys. I have 10 ways to do task 1, okay, because all these numbers are available to me to use, all right, to occupy my task 1, or to occupy the space of my first digit, if you want to call it that, because we are looking at how many 4-digit codes are actually possible for us to be able to form if each digit from 0 to 9 may be used any number of times. Okay, so I can use 0 here, I can put 0 here. Okay, that's one way. I could put 1, that's another way. I could put 2, that's my third. I could put 4, okay, I could put 5, I could put 6, I could put 7, I could put 8, and I could put 9. So it means I have 10 ways, all right, of representing task 1. Okay, that's for my first digit, for one of the 4-digit codes that I need. Now, if we go now to my second task, remember we are told if each digit may be used any number of times. So that means that in task 2, how many digits do I have available to me to use from my 0 to 9 digits? How many digits do I have available to me if each digit may be used any number of times? All right. Okay. So hopefully we see that we still have how many? 10. I still have 10. All right. Because why? The condition is that each digit may be used any number of times. So that means I do not reduce my number of digits from 10. I still have 10. when task 1, task 2 comes around. I still have 10 digits. Why? Because the condition clearly states if each digit may be used any number of times. So let's say if I used 1 here, I still can use 1 there. So that means I still have 10 available digits, because remember guys, we are choosing from 0 to 9. And how many digits do we have in total from 0 to 9? It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I have 10 available ways for task 1. What about task 2? I have still 10 available ways. Why do I still have 10 available ways for task 2? It's because the statement says how many 4-digit codes using digits 0 to 9 are possible if what? This is the condition that makes it that in task 2 I still have 10 available digits. If each digit may be used any number of times. So think about it. If 1 has been used here, all right, 1 does not fall away. 1 can still be used even in my task 2. Which is why I still have all 10 of my numbers remaining to be used. What about in task 3? Well, still, each digit may be used any number of times. So that means even in task 3, I still have how many numbers, guys? I still have all numbers available to use from 0 to what? To 9. What about in task 4, guys? What about in task 4? If each digit may be used any number of times, how many numbers do I still have available? I still have 10. Okay? So that means for each task, for my assembling of the 4-digit code, for my creation of the 4-digit code, these here are the ways that I have to be able to represent each task. So therefore, what do? I multiply the number of ways for each task. And what do I get? 10 to the power 4. What is 10 to the power 4? 10,000. So that means how many 4-digit codes can I be able to form from a 0 to 9 digits, where, as the condition states, if each digit may be used any number of times. Guys, the key is here in the statement itself. You see, once you are able to see, oh, if each digit may be used any number of times, oh, that means repetition is allowed. So that means my 0 to 9 digits can still be used for task 2. They still can be used for task 3. They still can be used for task 4. All right? Because as I think, okay, 0, I used here. Well, you know what? Because I can still repeat the use of 0, it means I still have 0 here to use. So it's not like 0 falls away. I still have all 10 numbers or 10 digits available for each task. So 10 to the power 4 then gives me 10,000. That means how many 4-digit codes can I actually form? 10,000 4-digit codes. 10,000 4-digit codes. All right. Now think about someone who's coming to your safe where you have chosen from 0 to 9 numbers, you know. And that's why it's like the probability of that person being able to, you know, crack your code, you know, it should be really 1 is to 10,000, really, you know, 1 over 10,000, which is really, really, really close to impossible. It's close to impossible that that person should come to your safe and punch in a 4-digit code that is exactly your code the first time round. You know, so yeah, I guess pins are safe, but you know, people nowadays, people are doing all sorts of things. My people, it's very scary. I hope we understand example 2, guys. The condition here, when repetition is allowed, we need to be able to spot the wording that points to when repetition is allowed when we are reading our statements in our probability problems. So when we see these things, if each digit may be used any number of times, then that suggests repetition is allowed. And when repetition is allowed, it means for each respective task, what are we actually saying? It means that the number of ways for each respective task will basically remain pretty much the same, and therefore we can actually use the exponent and then get our value. You see? Okay, I hope that is clear for all of us. All right, given what we see in the statement. So I'm going to say goodbye to example 2. I hope we get the concept though, when repetition is allowed. Are possible if each digit may be any number of times. Okay, so any synonymous phrase that alludes to repetition being allowed, we now understand what that actually, how that affects how we go about answering the question. Okay, all right. Let's turn over. If we came from when repetition is allowed, then we should be able to go to when repetition is not allowed. So let's check when repetition is not allowed. Let's check this out. This thing is saying when repetition is not allowed, when choosing from a group of different objects multiple times and repetition is not allowed, the number of objects we choose from is reduced by 1 each time a selection is made. Yeah. Singesi, English, Sekgowa. When choosing from a group of different objects multiple times and repetition is not allowed, the number of objects we choose from is reduced by 1 each time a selection is what? Is made. Okay. So yes, thank you, Mr. N. There definitely does matter, the order there, very important. So let's look at this one. Same problem, the wording slightly different. Now we are told here how many 4 digit codes using digits 0 to 9 are possible if no digit may be used more than once. Okay, I repeat, how many 4-digit codes using digits 0 to 9 are possible if no digit may be used? If no digit may be used more than once. Okay. When repetition is not allowed, no digit may be used more than once. So I'm sure you can see now that there's no repetition is allowed. So once again, 4-digit code means that we have how many tasks? 4. Okay, 4 events. All right. How many ways for each, or how many ways do we have available? All right. Generally speaking, using digits 0 to 9. Digits 0 to 9 means what? Once again, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. This is just, I'm doing this for people that, I really want to be able to see visually and then count how many ways, in other words, are possible. Do we have possible? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 ways. Okay. Now, how many 4-digit codes using these are possible if no digit may be used more than once? So let us all agree that to begin with, how many ways do we have for task 1? Obviously, we have 10 numbers available, so we have 10 ways in which we can represent task 1. But please now take note, guys. Remember that one of these numbers is used, all right? It is used in task 1. One of them is used, okay? So we choose that particular number, it gets used. So when we go to task 2, Can we use that number that has been utilized in task 1, given that no digit may be used more than once? Can we use it? No, we can't. Okay? Because here it is stipulated if no digit may be used more than once. So therefore that means for task 2, let's just say 0 is gone, okay? Because after task 1, 0 is gone. How many numbers do we have left? 1, 2, 3, 4, 5, 6, 7, 8, 9. We now have 9 numbers. For task 2, we reduce the total that we had initially to what? To 9. I hope that makes sense, guys. So that's why in task 2, we now have 9 ways available because 1 has been used. Why? Because we were told in the condition, if no digit may be used more than once. This dictates what we do. Then it means the next one, we have used 0. Let's say we used 1, gone. How many numbers do we have left now? We can count and then we can fill in 8. Then we use 2. Then we can count. How many do we have left? 7. So that means what? 10 times 9 times 8 times 7. So we take this, guys, we put this into the calculator, we get the answer. All right? And we need to write down, guys, the answer. We can't leave simply the answer as a product like this. We need to be able to write the answer that we get from the product. Okay, so there are 5,040 4-digit codes, guys, that we can get. 5,040 of them. Okay, yes, Starchrist, because we were told if no digit may be used more than once. What does that mean? It means there's no repetition. We cannot repeat that number that we basically used in the first task. We can't. It must stay behind. It remains in the past. You know, that's no repetition is allowed, guys. You know, when you have used something, you know, it's like this thing is like being in matric. Unfortunately, guys, you guys will do your matric and then you will leave matric. Even if you will go ahead and improve your marks in the future, but you will never be able to have the same matric group with the same people, with the same experiences, with the same age cohort that you are in right now as a matriculant. Next year, this thing will be a thing of the past. You know, repetition is not allowed. Repeating the same life experiences that you are having this year is not allowed. You know what I mean? Next year. So even though some of you may feel like, oh, I can't wait until I'm done with matric, I promise you, when you sit in those university walls or wherever you will be next year, you will look back and you will miss high school. You'll miss it with all your heart's content. I can promise you that. Just wait and see. No repetition is allowed. So I like this, guys. Don't forget this. When repetition is not allowed, the number of objects we choose from is reduced by 1 each time. So do you see what happened? Reduced by 1, reduced by 1, reduced by 1. Each time a selection is made. So that's why this happened there. 10 times, 9 times, 8 times, 7. Thank you, Natalia, for attesting there in the comment section. I love you a lot for saying, for supporting what I've just said. Yeah, you guys make, my words have power. So let's go to example 4. Let's look at this one, guys. So I hope that this example of 4-digit codes, when you looked at the statement, if no digit may be used more than once, how different this was when we were looking at the same problem. How many 4-digit codes are possible if each digit may be used any number of times? Such a different scenario. Bye, NK. It was nice having you. Have a good night and sleep well. Okay, example 4. How many ways can the letters of the word action be arranged? Letters may not repeat. Okay, now I like what they usually say about letters specifically. let's say that this question was asked and they said, how many ways can the letters of the word action be arranged? Okay. Generally speaking, and as has been generally accepted, words, all right, when they are given to us, they infer that letters may not repeat. Okay. Any word that you are given, the conclusion we make is that the letters may not repeat. Okay. Yeah. Letters may not repeat. So even if they don't say letters may not repeat, but you must understand that words by nature are that they do not repeat. Okay. So let's look at how many ways can the letters of the word action be arranged. So obviously we need to look at the word action. How many letters does the word action contain? It has 1, 2, 3, 4, 5, 6. So that means how many tasks do we have? 1, 2, 3, 4, 5, 6. Very important to do that. So this word action, it means we can arrange it in whatever way. It does not have to make sense, the word, when we put it together. It's just saying how many ways can the letters of the word action be arranged. So it's not like if the word does not make sense, then it does not qualify. No. Any word from these letters, okay, we're wanting to just know how many arrangements can we actually form from the letters of this word. Okay, where the letters may not repeat. And even if they didn't say where the letters may not repeat, the word itself by nature is one that does not what? Where the letters do not what? Do not repeat. So what do we say, guys, to begin with? How many letters do we have available for each word? I mean, for the word itself, how many letters do we have available in how many ways do we have available for each task? For the first tasks especially, we have 6 letters, thank you, available. Okay, then of course, one of the letters will be used, right, for our first task. One of the letters will be used for our first task. Then, how many words do we have available for our second task? The letters are reduced, as it says, guys. The objects we choose from is reduced by 1 each time a selection is what? Is made. Okay, start Christy, remember, the letters of a word, we need to just understand this. The letters of the word may not repeat, and even if they did not tell you that they do not repeat, words in and of themselves don't repeat. So yeah, with the words, we just need to be, be careful with those ones. Okay. But just take note of the statement. Always read the question and read what are the conditions stipulated for the particular question that is being asked. But of course, we'd say 4, 3, 2, 1. And what does that introduce us to, guys? It introduces us to this concept that we call factorial. All right. And we can actually say that 6 times 5 times 4 times 3 times 2 times 1. When we have a product of descending numbers from a particular number that descend, all right, by 1 up until 1, that the important part is that up until 1, then we can represent the product of these numbers by the number at the beginning, all right, which is the highest number, followed by an exclamation mark. This is what they would call an exclamation mark in English, right? But we say this symbol is called factorial notation. Okay, it's called factorial. It's a mathematical symbol. Okay, so the products that we have here that descend all the way to 1, all right, that pure arrangement that we have, the multiplying on numbers that are reduced by 1 successively till we get to the number 1, we call such products factorials, and they are indicated by the mathematical symbol, which is that exclamation mark in English. Okay, so please, guys, the final answer, all right, 6 factorial. In your calculator, you should be able to see the symbol in and of itself. And the examiners want you guys to be able to write down the answer, the actual number. They want you to write it down. So that's 720. They don't want you to leave your answer as 6 factorial. You will lose marks if you write your answer just simply as 6 factorial. You must write the actual outcome of the answer. Please, guys, don't leave it as 6 factorial. We want this answer. Okay? And guys, we don't go too deep into factorial. It's just important for a grade 12 learner to know that, yes, this, as we saw it, the multiplying of numbers reduced by 1 successively, till we get to the number 1, we call such factorial, and we use this mathematical symbol to basically represent factorial. This is only written, guys, when the descending multiplication or product gets all the way to 1. You will note that we had a descending multiplication all the way to 7 here, but we did not write factorial, okay? So it's when the descent of multiplication successfully, the reduction of numbers, the product goes all the way to 1, then we can actually write factorial, okay? Okay. Yeah. So let's align to this. All right, be able to write 6 factorial, and then let us then after that write down the answer. Okay, yeah. So I hope let's just do that. So if we do that, then we'll be good. Please do the repetition part once you are done. Repetition part. Star Christy, the repetition part is no different from this. Okay, it's no different from this, because remember, there's no descent with repetition. It just means whatever way we had in the beginning, it's what we retain, because there's no because repetition is allowed. Okay, yeah, repetition is allowed. But remember, like I said, with words, letters of words, okay, practically speaking, they don't do such when repetition is allowed. Yeah, letters may not repeat, and even if they don't write letters may not repeat, they will actually just say, how many ways can the letters of the word action be arranged? You should take it that the letters of the word cannot repeat. That's very important. Okay, so yeah, guys, yeah, factorials can be calculated by using the factorial button on the calculator. I think the factorial button is there on your calculator, your scientific calculator, so please be able to use that for yourself. Okay, okay, now I'm going to enter into this last part, and then that should be that for today. Guys, there's the probability aspect of the counting principle. I just want to go over the concepts. That's it for today. I don't want to go into the probability. In a future live, I'll do that with us, but for today, I just want to make sure that we get the whole concept of just the definition of the counting principle and that. Okay, let's look at this now. Restrictions. Okay, arrangements with restrictions. Okay, let's look at arrangements with restrictions. So restrictions, and sorry, forgive me for my beautiful handwriting there. Like I said, I think in my life past, I think I should have been a doctor, but like you can see, the writing just sometimes does not give teacher vibes at all. So restrictions on certain positions or grouping together, we're going to look at that. So let's look firstly at restriction on position. Let's look at this question. A restriction on position. How many ways can the letters... You do sound like a doctor. Thank you, Zenzi. You are so kind. You are so kind. My goodness. All right. How many ways can the letters of the word... How many ways can the letters of the word... Hi, Monster Chris. It's better than mine. Nonsense. Why are you making me laugh so late at night? How many ways can the letters of the word... And this is the word, guys. Equations. How many ways can the letters of the word equations Oh my goodness, Livia, calm down, relax. How many ways can the letters of the word equations? You guys are disrupting me, right? Okay. I'm just kidding. But yeah, you guys are disrupting me. Just a tad bit, okay? Don't mean in a bad way or negative way, but yeah. How many ways can the letters of the word equations? So the word equations. How many ways can the letters of the word equations be arranged if, now let's check this condition, if what? If the first letter must be an E. Okay, let's do this again. How many ways can the letters of the word equations be arranged if the first letter must, you see, they're saying the first letter must be, must be an E. We must have an E. Okay. Now, guys, deliberately in this question, the word itself has no letters that are repeating, and that is deliberate. Okay. We are going to get to when we have letters that actually appear more than once. You know, the same letter appears more than once in a word, but we have chosen a word that has letters where the letters don't repeat themselves anywhere in the word itself. All these letters, they are unique in the word. There's no other E, there's no other Q, there's no other U, there's no other A, there's no other T, I, O, N, S. Do you get the point? So for now, because we are doing an introductory thing on counting principle, we want to just understand the concept. We want to get the basic understanding in. So, and please, guys, if there's something that you're not sure about, please ask me the question, okay? So I'm going to repeat the question again. We're looking at restriction on position. It says, how many ways can the letters of the word equations be arranged if the first letter must be an E? So let's first start from the basic as we answer this question. Firstly, how many tasks do we have? All right, and I'm sure now you can see, guys, we just make sure we write those spaces so that we can be able to accommodate our tasks and then be able to represent the ways. So we have 9. I love it, you guys. 1, 2, 3. I just want to confirm, in case you guys are just like you're pushing me under the bus. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes, okay, we do have 9. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, all right. So confirmed, we do have 9. I've also counted, guys. So that is such an amazing accomplishment. Okay, now, how many ways can the letters of the word equations be arranged if I counted 9 off page 1, 2, 3, 4, 5, 6, 7, 8, 9. Hi, Wena, Natalia. I'm going to smack you. Okay, how many ways can the letters of the word equations be arranged if the first letter must be an E? Now, this here is where we start, guys. We start here because it's a very important place to start. When we have some sort of restriction where it's like it's a must, I don't like restriction. I don't know about you guys, but I tend to not like it so much when I'm restricted to do, I'm restricted in the choices I need to make, and there's sort of like limited things that I can do. I don't particularly like it, but I must say I've learned to see the wisdom in doing that, because having restrictions in life is so key, hey? That is basically the heart. A heart of discipline is laced in restriction, and it's not unhealthy restriction, but it's healthy restriction, which obviously then allows you to be able to have greater freedoms in the future, greater freedoms in the future, but we don't usually perceive it in the moment, So anyways, if the first letter must be an E, guys, Olivia, same restrictions. Oh yeah, totally, guys. Okay, we get the point. Now, if the first letter must be a what? Must be an E. So that means let us go directly to the restriction here. If the first letter must be an E, so that means in the first position, or for my first task, I only have one option where my letters are concerned, and that is I can only have a what here in the first position for my first task. I can only have an E. All right? Okay, I hope you understand that, guys. So how many ways do I have available, okay, for my first letter? Okay, in my first task, I only have one. Okay, one way, guys. Yeah, talk about just one. Because the thing is saying here, if the first letter must be an E, so this must be an E. It can't be a U, it can't be a U, can't be an A, can't be a T, can't be an I, can't be an O, can't be an N, can't be an S. It must be an E. So the minute I say task 1 has one way, what does that then mean? It means E is gone. Because remember, I know with my words, is repetition possible? No. Can't repeat with the letters of the word, right? Now the thing is, you guys are gonna say, but it did not say so, sir, in the statement. But remember, what did I say about a word? What do we mean when we talk about a word? You know, does that mean repetition or no repetition? So for a word and for its letters, okay, even if we are not told explicitly, we know exactly that for a word, repetition, cannot happen. Okay? Cannot happen. So that's why then we know here it's 1. Okay? Now, how many words do I have left? That's the $1 million question. E is gone. Alright? Because repetition is not allowed. So how many letters now do I have? Okay? I hope you guys know. Because I want to check now for my task 2. Task 2. Okay. One letter is gone, E is gone. How many words do I have left? 8. So that means for task 2, I have 8 available what? Available words that I could actually utilize for task 2. 8 available words. All right. So I can say 8 here. But remember, 1 will be used up. And then how many words do I have left here? Because repetition is not allowed. Okay, for a word. We know that. We know that it's implicit, it's implied in a word. So that means 7. You guys get the point. You guys get the point, don't you? You guys get the point, don't you? You guys get the point, don't you? You do, right? Guys, I hope you really do. I hope you do. So that means 8, 7, 6, 5, 4, 3, 2, 1. Livia, you are not even in grade 12. You are... Livia is not even in grade 12. Livia, no, it's fine. Livia shouldn't get it. I actually am fine with Livia not getting it at all, actually. Like, I am more than happy to move on right now. Natalia, don't worry about Livia. Livia is not allowed to get it. Livia is not allowed to get it. Livia just wants to get ahead of, like, she wants to have the... You can cry boo-hoo-hoo all you want, Livia. Livia is not allowed to get it. Okay, so that means, you see, Livia, sometimes certain things are veiled upon your face so that you can focus on what you need to... No, I'm not choosing at all. Yeah, I'm not choosing at all, right? She wants to make it to matric armed and ready. Oh, wow, what a soldier. What a soldier. And Natalia is like giving you free space and liberty here to exercise your power here. Okay, guys, like I said, remember, we said the first letter must be an E. So that means we are restricted only to E. But remember, when we choose to basically place the letter E here, how many letters of the word equation do we have left after choosing E? 1 is gone. So how many are left? How many letters are left? We have 8. Remember, for task 2, all right, we can choose one of 8 letters to basically put here for this task. Remember, that's why we write 8. Okay, we write 8 Any one of the 8 can be used here. But the minute 1 is chosen, all right, 1 falls away, then we are left with how many to choose from now? 7. Okay? But then 1 will fall off, and then basically we're left with how many for task 4? We're left with 6. And so it goes. We reduce each by 1 for each task. All right? Because why? Repetition is not allowed. Okay? So I'm sure you guys understand. You can times as per the definition of counting principles. So that means our answer is actually 8 factorial if you want times which what? This one. But you know almost 1. Anything multiplied by 1. And then make sure, guys, you put this in your beautiful calculator and get the actual answer. Thank you, Mr. N. Mr. N there, 40,320. Miss Buddha, thank you so much for that, Rose. Very welcome, Rose. I really appreciate it. You are the bestest. Yes, Buddha, Boo, Miss Buddha. Thank you, Natalia, as well. Natalia is like, I can't miss out on the rose action. I need to pull out a rose. Okay, thank you so much. Really appreciate that. Yeah, thank you so much, Mr. N. Guys, Mr. N, a former student of mine from back in them days. He's actually got a, he's heading a program there, the Maths Confidence Club. And you know, if you guys have people that you know who may be in matric, maybe struggling with mathematics, technical maths, math literacy, yeah, he's the guy, he's the man. You can go to his you are more than welcome to go to his profile there. Mr. N, he's the one that basically commented there with the 40,320. He's doing some phenomenal stuff. He's hosting classes, both online, physically, you know, at his where he's residing. You know, you can definitely get more of the information pertaining to what he's doing. But yeah, he does do one-on-one. Yeah, and I think, yeah, all sorts. But you can get more info from him. Definitely an amazing man, definitely an amazing guy. And I love the principles and the heart that drives what he does more than anything else. So, yeah, I can proudly say he's one of the people that I had the opportunity and privilege of being able to, at some point, touch, teach, and influence. So it's so good to see him here in my life, but also at the same time the impact and the positive footprint that he's leaving in the lives of so many young people in the country and also like in his locality as well. Yeah, so guys, definitely someone that you need to follow there. The Maths Confidence Club. If you want to restore your confidence back in the maths, he's the man, Mr. N. Sure thing. Okay, let's go on, guys. Before I get too emotional, I don't want to be crying here, you know. I don't want to cry. Yeah, okay, forget about that. The grade 9 and the grade 11. Yes, definitely. Yo, it's back in them days. It's funny how things happen and they cross paths like that. Okay, let's move there. Guys, hopefully we get this one. 8 factorial times 1. It's beautiful there, né? It's happening nicely. So we have 40,320 ways in which we can arrange the word equation, where we restrict basically the first letter as E, you know. So I hope that's clear. Look at this one. The next question says the first letter must be an E and the last letter must be an S. These people. The first letter must be an E and the last must be an S. Thank you so much, Miss Buddha. Thank you so much. The first letter must be an E and the last letter must be an S. So once again, we are talking about how many letters how many tasks, sorry. Let's start about tasks. And the tasks correspond with the letters. So 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, 8, 9. Orlando, Mr. N, don't give out too much details there. Look at these people. They must stick to that. Matters as a game host. It's fine. But yeah, keep things low key there. Okay, so the first letter must be an E, and the last letter must be an S. Okay, so what does that then mean? Because now we are restricting things here, aren't we? The first letter must be an E, and the last letter must be an S. Okay, so if we are saying that, Star Christie, ooh, Star Christie, story star. Okay, yes, definitely. First letter must be an E. So that means once again, we start with the restrictions, eh? And guys, it's always good to start with the restrictions. Start with the restrictions, and then everything else comes off from there. So start with the restrictions first. So the first letter must be an E. That means one way in task 1, and then the last must be an S. Very good, Star Chrissy. So that means we are going to write 1 at the end as well. But remember, every time we write, what are we doing? Reduction. So the 1 letter is gone, second letter is gone. So that means how many are left? How many letters are left if 2 are gone? We had 9 in total. So E is gone, S is gone. Thank you, Zinzi. We have 7. So that means we are going to say 7. And then every time we go to the right, what happens, guys? Star Christie, Goodness, Natalia, Zinzi, guys are amazing. So then that means for task 2, 7, task 3, 6, task, very good, Livia, we reduce 5, 4, 3, 2, 1. Ding, 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 ding. You know, guys, this is like our highest level. Thank you so much, Miss Buddha. This is so generous and kind of you. That means this year, that is the highest level we want to be getting in mathematics, guys. You see, I think this is like a prophetic thing here that's happening here. You know, the highest level that we want to attain here. So 7, we want 7, level 7. All right, so let's do it, guys. So that's there. All right, so that means, if you think about it, having set up what we set up here, we multiply. So that means this is 7 factorial. Now, you have 1 times that 1. But I mean, guys, 1, what does 1 do? What effect does 1 have? You know, remember, 1 is an identity, what is it called? They call it an identity element. All right, and what does an identity element, the identity element 1 do? It basically retains the identity of whatever other number we are multiplying by. So 1 basically just makes sure that you retain your identity. Okay. So you know, I'm just understanding this now. Star Christie, that's beautiful. I'm glad you're understanding it now. So I'm also glad that these are some of the things that make me believe that, you see, that this is just God's grace in operation. It can't be anything else. You know, I'm a mere human being just like you. So if you're understanding this now, I'm very happy, and I hope that you will take confidence from this understanding, and then you will just fly. Go and attempt questions, go and do more exercises. I'd really recommend going to the textbook and just doing the textbook exercises, so that you can then reassert your conceptual understanding. Then after that, you can just go and do exam papers. Then you'll see that at least your foundation, your basics are placed. They are set. You are set. You are good to go. You know, and the Mind Action Series textbook is quite good. The new one, with the exercises. You know, 7 factorial. Thank you so much, Mr. N. We don't forget, because remember, if we don't write this answer, you know, thank you, Natalia. So grateful there, guys. You guys are so generous today. Like, I really appreciate it. Like, thank you. Thank you to all of you. Miss is it Mrs. Buddha? Thank you as well. Thank you, Natalia. 5,040, guys. There it is. 5,040. Mr. N is our automatic calculator. Yeah, you can say that again. Automatic calculator, sir. I mean, what do you expect? I mean, he's one of the best in the game. Second letter. Okay, let's look at this one, guys. Let's look at this one. Second letter must be a Q. The second letter. Okay, so let's take note, guys. Second letter must be a Q, and the seventh must be an O. Second letter must be a Q, and the seventh must be an O. Okay, so once again, 1, 2, 3, 4, 5, 6, 7, 8, 9. Whose second letter? Second letter must be a Q. Q? There's only one of y'all. Q, one of y'all. Q, one of y'all. Alright, so there's only one of Q. So obviously, second letter must be a Q. So that means what? I can just see Star Christy saying, yo, Star Christy, yo, mess around. It's like I could see you, Star Christy, like already typing in, and you definitely like just you delivered there, delivered in the moment. So yes, definitely second letter must be a Q. So yes, definitely that's 1. Okay, in that task 2. Then seventh letter must be an O. All right. So seventh letter. Zinzi, I'm not gonna say anything yet. Me's not gonna say anything. Me's not gonna say anything. Me's not gonna say anything. All right, yeah, because like I said, I'm just trying to develop this from basic ground up. You know, yeah. We're gonna arrive there. The most probably may not happen today, but I mean, like, yeah. For now, I'll just speak to what I've said. I think it will be enough for me to speak to what I've said, but above and beyond that, there's still yet more to come. Okay, so this is probability part 1, probability part 2. Let's say tomorrow, same time, same place, same people, same arrangement. 10 p.m. again tomorrow. See each other for the next episode of Probability with Maths is a Game. Okay, second letter must be a Q, and the seventh letter must be an O. Seventh letter. So seventh letter is here. Must be a what? An O. So that means restriction again there. Natalia, you had to write that down. You are hilarious. Okay, so there. Okay, so that's one. That's 1, right? Okay, let's focus, guys. Then we have how many letters left? Because we took the Q, we took the O. So how many letters in total? Yes, 7, guys. Now all we do with that is we just say 7. Guys, doesn't matter that we have 1 there. There was a restriction for obviously task 2, which is fine. Then we say 6 for task 3, 5, 4, 3, 2, 1. You see? You just do that. Yeah, you see? You feel me? 2, 1, 0. No, I'm just kidding. Okay, don't write 0, guys. Yeah, because remember if you would. Okay, so we get the point there. Then of course the 1 times 1, that will lead us to 1, but then we know we've got 7 what? Because we got 7, the 6, the 5, the 4, the 3, the 2, the 1. That's 7 factorial. You multiply that with the 1 and the 1. It does not really have an impact, of course, guys. So we just say what? 7 factorial. Which 7 factorial we found earlier on is 5040. So how many ways can letters of the word equation be arranged? If the second letter is Q and the seventh letter must be an O, we have 5040, guys. 5040 amazing ways. Right? Okay. Sounds good enough, God? Let's hope it does. Hope it does. Hope it does. Yeah. Yeah. So these are good. These are nice. Okay, let us move forward to the next sweet question. Okay. Same letter. The first letter must be a vowel. Ooh. Do we know what a vowel is, guys? Do we know what a vowel is? I wonder, do we know what a vowel is? Good, guys. I'm glad you guys know what a vowel is. Okay, vowel is definitely that. A, E, O, U. A, E, O, U. Da, de, di, do, do. You know, like, yeah. A, E, I, O, and U. So if we go to equations, how many vowels do we have? The first letter must be a vowel. How many vowels do we have? Because the first letter must be that. How many vowels do we have in the letter equations? So in the letter equations, we have E, which is 1, U, we have A, we have I, we have O. So that's 1, 2, 3, 4, 5. Man. And we do know that there are 5 vowels generally. So that means we have all our vowels there, like all of them, you know, all of them. So if the first letter must be a vowel, what meanest that? Let us go and check. So we go ahead again and we write down 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, of course. Then our first letter must be a vowel. But now, guys, since our first letter must be a vowel, we need to take note of something here. There are how many vowels? There are 5 of them. Because remember, you could have an E there, you could have a U there, you could have an A there, you could have an I there, you could have an O there. Any of those letters could feature here. All right. Okay. So that is why we write 5. Yes, Livia. First line should definitely be 5 because we have how many vowels? 5 of them. So in task 1, there are 5 ways. Based on this condition here, the first letter must be a vowel. We know that we have 5 of them. So we have 5 available options, which means we have 5 ways. All right. I hope that makes sense, guys. But remember, even though that is the case, all right, if one of the vowels would be utilized, obviously for task 1, though we know we have an option of 5. If one of the vowels is used and repetition is not allowed, that means how many letters in total do we have available out of the entire word? Okay, very important, that one. Thank you, Ms. Suda. We have 8, guys. We have 8 left. Okay, so even though we know that there are 5 vowels, right, we know that we reduce one of the letters, which is one of the vowels in this case. But then how many letters do we have available to use? All right, that means we have 8 of them. So that's why here we are going to write 8, 7, 6, 5, 4, 3, 2, 1. Lift off. Some of you come end of this year will be counting like this towards countdown, New Year's countdown, as you'll be ushering in a new year. Some of you guys will get level 8 as well for your mathematics, level 8. You must ask Mr. N what level 8 is in mathematics. Level 8 is such a beautiful level to attain in maths, right? So let's get this. So it's 5 times 8. So it's 5 times 8 factorial there, guys. All right, beautiful 5 times 8 factorial, and then our human calculator has just entered into the building, guys. Like such phenomenal stuff. I think Natalia is coming shortly, just after the human calculator. Natalia is also sort of like getting her human calculator-ness going down there. So guys, you then obviously get that beautiful I remember when our minister used to call these numbers, It used to be a big struggle. Even our former president, with the pronunciation of these numbers, very huge struggle, a very huge struggle. But hopefully we can actually